So in this talk, we will see how to make use of 89C51 RD2 microcontroller based system. As you can see, the board is designed with this controller, which is a 40-pin DIP package populated with several peripherals. The various parts of this board is, one is this controller power supply is provided through USB. So computer's USB port, which supplies 5 volts 500 milliamperes of current, can source this board. Otherwise, there is a adapter which you can connect it here, DC adapter, 9 volts adapter. If you connect it here, then this 9 volts DC is regulated by this 7805 IC, where the output of this regulator is 5 volts, will be provided on this entire board. So the power can be supplied either through computer's USB, or if you have an adapter as a standalone, can be provided through this DC power supply, external DC power supply. As far as programming of this controller is concerned, it is programmed through RS232 port, serial port, which a computer has RS232 port, where the voltage standards are plus 12 and minus 12 volts. The same thing can be connected over here. Since microcontroller is operating on 5 volts, in order to interface the serial port of the microcontroller to the computer serial port, there is a DC to DC converter. So programming of the controller is done with the help of the serial communication. Other peripherals on the board is, two switches are interfaced on the port for giving the inputs. 4 LEDs are connected on the ports for writing various programs to display on and off the LEDs. There is a reset switch. The crystal for this microcontroller is 11.059 megahertz. There is a DC motor driver IC is there on the board, L293D. This can be used to drive either one stepper motor or 2 DC motors. You can connect the DC motors or stepper motors over here. Whenever you are using DC motors or stepper motors, you must use the external power supply. 12 volts DC power supply, you will have to connect it here. So the motors are powered by using this supply, not through USB. There is a relay connection is available. There is a BC547 transistor. This transistor will drive the relay. Again, if you want to use the relay, then DC power supply is required. There is a buzzer is connected, 5 volts operated buzzer, which is connected to the microcontroller. There is a LCD connector over here, which is 16:2 LCD can be connected here, which is a text LCD for writing various programs to display the contents on the LCD. All the 4 ports, port 0, port 1, port 2, port 3, all of them are provided on the 5:2 FRC male connector. So for expansion purpose, all 4 ports are available on the slot. Let us look at the circuit diagram of this board, how this board is designed. First of all, this board is designed by using 89V51 RD2 microcontroller, which is a 8051 architecture. It's a DIP package, 40-pin IC. Any minimum system design means at least first the VCC and ground should be connected. So pin number 20 is ground, pin number 40 is VCC. The second interface to any controller is the crystal. So one should connect the proper crystal. Though this microcontroller can work up to 40 megahertz, uh, in this board 11.059 megahertz crystal is connected to pin number 19 and 18, and two biasing capacitors are connected as recommended by the manufacturer. So in this kind of interface is enough to make the microcontroller to work. But however, since this controller has to be programmed, so serial port is used, that is pin number 10, that is P3.0 RXT, and pin number 11 port 3.1, which is TXT. These two pins are connected to computer's serial port, that is MAX232 IC is used, which will convert the TTL signals into RS232 form, that is plus 12 and minus 12. So computer serial port is connected on X2 connector, that is pin number 2 and 3 of the computer serial port is connected to this DC to DC converter. This DC to DC converter is operated on 5 volts. So pin number 16 is VCC, pin number 15 is ground. So by using these 4 capacitors, that is C6, C7, C8, C9, 10 microfarad capacitors, where this DC to DC converter will build up the charge, which will convert 0 volts to plus 12 volts and 5 volts into minus 12 volts. So 1 and 3, as you can see, is connected with this 10 microfarad capacitor. 4 and 5 is second 10 microfarad capacitors. But interestingly, pin number 2, positive is connected to pin number 2 and negative is connected to 5 volts. And exactly opposite, pin number 6, negative is connected to pin number 6 and positive is connected to ground. So this IC will convert these TTL signals of TXT, RXT signals into RS232 standard signals, that is plus 12 and minus 12 volts. So computer serial port is connected here to program this microcontroller. This program, the programming of this controller is done with the help of in-system programming. So there is a EA bar signal is there. This EA bar signal always has to be connected to VCC so that this in-system programming will work. So computer serial port programming will program this controller when this EA bar is connected to VCC. So this is the minimum system design. But otherwise, as far as the other interfaces are concerned, port 0 output port is a floating. So obviously that port has to be pulled up. So a 10 kilo ohms resistor package, single inline package is connected, entire port 0 is connected to VCC by using these pull-up resistors. Then about the other features is there is a reset switch, and since the reset pin of the microcontroller, that is pin number 9, which is active high, so this particular pin is connected to the ground by using this resistor, that is R9. And whenever this switch is pressed, reset switch is pressed, this particular pin is connected to VCC so that active 5 volts will reset pin will get it. Otherwise, in normal operation, when the switch is open, this pin is connected to ground. The power sources for this board is, one is through USB connector. Computer's USB port can be connected here so that 5 volts is connected. Second source is by using this jack, 12 volts DC adapter can be connected here so that this regulator will give output 5 volts constant. The input of this DC adapter is also used to drive the DC motors or stepper motors. That is, as you can see, the power supply of this DC motor driver, that is pin number 8, is connected to plus 12 volts. So for this driver IC, the power is coming from this input. Similarly, There is a relay driver is there by using BC547 transistor. Even the relay connector is also connected to the plus 12 volts power supply. So plus 12 volts power supply is essentially required. One is for the DC motor or stepper motor driver, other is the relay driver. As far as input output functions are concerned, there are two switches are there on the board, S1 and S2. S1 is connected to port 3.2 and S2 is connected to port 3.3. Whenever S1 is pressed, it will be connected to ground, otherwise the pin is at the floating state. Similarly, whenever S2 is connected, pressed, then pin 3.3 is connected to ground, otherwise S2 is on floating state. There are 4 LEDs are there on the board which are connected to VCC. Anode is connected to VCC. Cathode is connected to microcontroller port by using the current limiting resistors, that is R10, R8, R7 and R3 by 330 ohms resistors. So port 1 of the microcontroller 1.0, 1.1, 1.2 and 1.3 are used for driving the LEDs. The board is also interfaced with a LCD. LCD is a text LCD, 16 by 2 LCD. There is a 16 pin connector. Pin number 1 is ground, pin number 2 is VCC. Pin number 3 is again connected to ground by using some 4.7 kilo ohms resistor, which will control the contrast of the LCD. Then port 4, pin number 4, 5, 6, these are handshake signals. That is, pin number 4 is connected to port 3.7, which is a register select signal. Pin number 5 is connected to pin 3.6, which is read oblique write bar. Pin number 6 is connected to pin 3.5, which is enable signal of the LCD. The data bus of the LCD, that is pin number 7 to 14, D0 to D7, is connected to microcontroller port 2.0 to 2.7. In short, the complete data bus of the LCD is connected to microcontroller's port 2, and handshake signals of the LCD, that is RS, read oblique write bar and enable, is connected to 3.7, 3.6 and 3.5. There is a power LED on the board which is connected to 5 volts, other end is connected to ground. The motor driver is there on the board where L293D IC is mounted, which is a 16 pin IC. There are 4 port lines are connected to the driver IC. So the output of this driver IC, either you can connect it to DC motors or one stepper motor. The interface requirement for L293D is as shown. The inputs are 1A, 2A, 3A and 4A, and outputs of this IC is 1Y, 2Y, 3Y and 4Y. So the microcontroller's port 1.0, 1.1, 1.2, 1.3 are connected to this L293D IC, and the outputs which are there on pin number 3, which is 1Y, 2Y, that is 6, and 3Y, which is pin number 11, and 4Y, which is pin number 14, are connected on this 5-pin connector. So Q1, Q2, Q3, Q4 can be connected to 2 DC motors. For example, Q1 and Q2 is connected to one DC motor, Q3 and Q4 is connected to other DC motor, or Q1, Q2, Q3, Q4 are connected to one stepper motor. Pin number 1 is 12 volts power supply is available here, mainly for stepper motor. So stepper motor requires 5-pin connection, one VCC, 12 volts and 4 outputs of the motor driver IC. To enable this L293D IC, pin number 1, which is the enable pin, and pin number 9, which is again an enable pin. So this 1 and 9 are connected to port 1.4. So before writing the data to the L293D, you have to enable pin number 1.4 so that it act as a chip select signal to L293D motor driver IC. There is also a provision for interfacing servo motor on this board. So you can use this 3-pin connector for interfacing the servo motor. Basically, you need to generate a PWM signals on port 3.4. There is a buzzer which is mounted on the board, which is connected to port 1.5. Serial port is also provided on COM port, so that in case if you are interested in interfacing either Bluetooth or Zigbee, then without using this DC to DC converter, you can get TXT and RXT signals of TTL voltages, so that Bluetooth and Zigbee accepts TTL signals. If you want to interface a relay, the relay requires since more than 20 milliamperes of current. So the BC547 transistor is provided here. So you can connect the relay here. Other end of the connector is connected to 12 volts, and there is a freewheeling diode to discharge the back EMF currents. The BC54 transistor is interfaced to port 1.7. All the 4 ports, that is port 0, port 1, port 2 and port 3, all 8 lines are provided on the connector as shown left side, that is 1, 3, 5, 7 are the even pins and 2, 4, 6, 8 are the port odd pins. Pin number 9 is VCC and pin number 10 is ground. So all 4 into 8 IO lines are available on the 5x2 box connector. So this is as far as the features which are available on the board is concerned. Similarly, if you look at the placement of the components, the IC1 is your microcontroller, that is Philips 89V51RD2, which has a in-system programming feature. The USB is available here for power supply, and for programming the microcontroller you have a RS232 9-pin D-type female connector is mounted. 11.059 crystal is mounted here to give the clock to the controller. 2 biasing capacitors of 33 picofarad are there, C3, C4. There are 4 LEDs which are interfaced to the microcontroller are available here, LED 2, 3, 4, 5. And 3 switches. One is the reset switch, then S1 and S2 is mounted here. Then to interface the motor, the L293D is there, where motor can be connected here, and this is the DC adapter. Similarly, LCD can be mounted here. The direction of the LCD is towards the board. You have to mount the LCD. So direction is very, very important while connecting external connectors to the board. All 4 ports are there on this 5x2 FRC male pins. And as far as the connectors are concerned, the motor connector is here, serial port connector is here for TTL standards. For RS232 standards, it is available here. In-system programming connector should be always closed, that is here, which is mounted here. And servo motor, DC servo motor can be connected here. The relay driver, that is a BC547 transistor is here, and the relay connector is here. Similarly, the buzzer can be connected here. And the port 0 pull-up resistor SIP package is mounted here at 10 kilo ohms, where pin number 1 of the SIP is here. So this is as far as the placement and mounting the components are concerned. The precautions about this board is never consume the power more than 500 milliamperes when you are using the USB as a power supply. Then programming is done through RS232 port. Make sure ISP jumper is closed, and while programming always first connect this USB power supply, connect the RS232 cable. This jumper should be placed, and press the reset switch. And once the programming is done, then again press the reset switch so that your application program will work. So that is as far as the interfacing of this board to the computer is concerned. Let us look at the data sheet of the microcontroller. In this data sheet, one should carefully look at the important pins. One is, as you can see, the package is significant, though there are various packages are there for this microcontroller, but we are using the package which is a dual inline package. So whenever you insert any IC, we always see the pin to pin compatibility. Whereas functionally other packages like PQFP package is there, but then RLCC package is there, but you see the number of pins. Here the number of pins are 44. Then the pin functions also, they are different. Here pin number 1 is P1.0, but here pin number is P1.5. So functionally it is same, but they are not pin to pin compatible. So we are always talking about 40 pin dual inline package of 89C51 RD2. So in this package, as it shows, pin number 20 is ground, pin number 40 is VCC. Then there is a EA bar pin, that is pin number 31, which will decide the in-system programming. That is the pin which is recognized by the microcontroller whenever you reset, so that it will accept the application program from the computer. So the flash memory of this controller is programmed. Then about the crystal, as you can see, pin number 18 and 19 is connected with the crystal. So once the crystal is connected, ground is there, VCC is there, reset is active low initially. Whenever you want to reset, it has to be active high. And EA bar is connected to VCC, then the microcontroller will be start working. Only you can download the program. So now the next question is how to write a program for this microcontroller. You should have either assembler or the compiler. So we will see first a simple assembler, which is this assembler, which is 8051 assembler, where you can write the assembly language programs. And then later on, eventually, we will see how also how to write a C programs. As far as this assembler is concerned, this also has features for debugging. That means once you assemble the program, you can also execute the program by step in, that means single stepping, or you can step over, that means you can skip the function, or you can step out, that means you can come out of the function, or you can run the program up to a specified line, or you can run the whole program in one shot, or you can insert the breakpoint so that the program will be executed up to that point, or you can reset your program so that the program will start executing from the first instruction. So these are the various features for verifying the program, though you does at this point of time if you doesn't have the kit, but still you can verify the program syntactically as well as logically. So this is just a simple program. The program is, let us say, you want to switch on or switch off a LED. Whenever you want to switch on or switch off a LED, that means whenever you want to interface any LED to the microcontroller, one should see the electrical characteristics. Electrical characteristics means, say for example, if the LED requires, so let us say 10 milliamperes of current, does the port pin of the LED, the port pin of the microcontroller can source that much current or not? So that means what is the operating voltage of the microcontroller, then how much current the microcontroller can source or sink, right? So that is important. As you can see, for example, the sinking current is around 20 milliamperes of current on port 1 to port 3. So that means we prefer to interface LED which is in a common anode form, so that it can sink, controller can sink up to 20 milliamperes of current. So let us see how to write a program where, assuming that the LED is connected on port 3.4, which I explained in the circuit diagram, right? Then write a program to blink the LED. Okay, so in assembly language, first let us you consider this as a first editor to write the program. Just to explain about the program, ORG statement is to define the address where this instruction is going to be assembled. So this is a directive. So as we know, whenever we reset the microcontroller, the program counter will be loaded with the address 000. So in 00 location, we always say absolute jump to start. That means wherever your main program is starting, that jump address we store it here. Then other locations, what we call as the interrupt vector table, like 003, 00B, 13, 1B, 23. These are the reserved locations because these locations are used by other interrupts. Since at this point of time we are using only reset vector, other interrupts we are not using. So we are not using these locations. Simply we said return from interrupt. Okay, so when the absolute jump is made, the program will start executing from this instruction. The first instruction is clear accumulator, and the purpose of this loop is to clear the contents of the RAM, internal RAM, the first 128 bytes. So we have initialized as a pointer, R0 is loaded with the hexa value 7F, hash 7F means it is the immediate value, H means hexa value, which will act as a address. Then move at the rate R0. That means R0 has the address. So it is a indirect addressing. So the contents of the accumulator will be moved to the memory location whose address is specified by R0. So since accumulator we have already cleared, so 00 will be stored in memory location at 7F location. And then we are saying decrement jump if not 0 R0 to the address, specified address. That means every time we are decreasing the address from 7F to 7E, 7D, 7B like that till 00, this loop will be executed. That means 00 to 7F, the memory location will be cleared 0. This is just a program to explain that how to clear the contents of the RAM space. Second initialization of any program is the stack pointer initialization. As we know, stack always is used for to push the return address as well as to push the some of the contents of the CPU registers. So we want to initialize the stack here because here the stack grows. So stack pointer is initialized with the hash 30H address. Then program status word is stored with 00 so that we are selecting the bank 0 register selection. Then since we want to use the port 1, if you want to switch on or switch off the LEDs which are connected on port 1, so port 1 has to be made as a output port. So if you load 00 to P1 register, that means the port is configured as an output port. The program is just to switch on or switch off a LED which is connected on port 1.0. So set bit of port 1.0, then some call a delay function, then clear port 1.0, then call a delay function, then long jump to again. So this will be keep on executing. So delay program is move R1 register with FF, move R2 register with FF, decrement if R2 till it becomes 0, it will be in the loop. Similarly R1 till it becomes 0, it will be in the loop. So 255 into 255 times this loop will be executed and it will return. And once this loop is finished, then it is in the infinite loop because here you said this function should be executed. So in short, writing a assembly language program is nothing but the first part is interrupt vector table initialization. Second part is clear the contents of the RAM space. Third part is initialize the stack pointer so that your function return addresses will be pushed on the top of the stack. Fourth point is initialize your program status word so that the bank of registers will be selected. And the fifth part is if any peripherals you are using like ports or timers or interrupts, whatever, any peripherals if you are using, hardware initialization has to be done. So this part of the program is usually common for almost all the applications. After that, whatever is the functionality of the program, you write it, and then if you are using any functions, then you call them from the main program. And to tell the assembler that this is the last instruction, use a AND directive. So once you write the program by using this editor, then there is a option called assemble the program. When you assemble the program, the output window should say that there are 0 errors. That means the entire assembly language program is converted into a hexa file, Intel hex file format. Okay, so that's all. As far as writing a program and converting assembly language into hexa file is concerned, you can make use of this assembler. This assembler also has some features where what is called uh, logically verifying the program by using single stepping. So as I explained earlier, it has various options, like as you can see, you can step in and execute the program step by step. But before that, whenever you compile your program, you can also uh, view, right, some of the CPU registers. Say for example, if you want to see the registers of the CPU, as you can see, accumulator, B register, R0 to R7, stack pointer, program counter, DPTR. So you can view the contents of these registers whenever you execute a program. Similarly, if you want to view the ports, say for example, in our case, we are modifying the contents of port 1. So you can also view the contents of the ports. So similarly, you can watch the memory, internal memory, external memory, or watch window. If you have any variables, you can watch those variables on the screen. So now to simulate the program, either you can start the simulator, right? So now, as you can see, the cursor is indicating on the first instruction, because 000 is the first instruction. Now if you execute the program by single stepping, if you say step into, then the first instruction is executed. As you can see, it has made a jump to the start location, and you can see the program counter is also modified. Then as you can see, first instruction is to clear the accumulator. So if you execute one more instruction, accumulator is cleared. Now if you execute this instruction, R0 will be loaded with 7F. As you can see, 127 is loaded in R0. Later on, if you execute this loop, then R0 will be keep on decrementing, and then will clear the contents of the memory location. If you want to skip, because if you keep on executing, then you will have to execute it 127 times. Instead of that, in debugging, there is options just to step out of this function. So you can always execute by step out of this function. And if you want to stop this thing, you can always say stop. Then wherever it is currently executing, it will stop execute that program. So if you want to run the whole program in one shot, then as you can see, continue. Then this will execute the program in one shot. The whole program will be executed. So this is how you can logically verify the functionality of the program by using the simulation environment. Once you confirm your simulations, then you can go for loading the program actually on the board. So for that, we will use some another software, what is called Flash Magic software. So this software is a third-party software, which we will see how to program it. So programming of the microcontroller is done with the help of the Flash Magic software, which is a open source software freely available. This is the first menu. As you can see, first one has to select the device. This software supports so even ARM processors, ARM Cortex processors, and as well as 8051 controllers. Since on our board we are using 89V51RD2, so select this microcontroller. Then COM port 1. Since the computer serial port is COM port 1, if you have any doubt, then you should go to the control panel, then look at the device manager. In device manager, see the port address. If you see the port address, it should say COM1. So all of you look at your computer, see what is the address of the serial port. If it is COM1, then in FlashMagic also you select COM1. If computer doesn't have serial port, then you will get a USB to COM port converter. So once you connect that converter, go to again to the control panel and device manager, where it will show what is the address of the COM port. So once you know the address of that, exactly you select that COM port address only. Since in our case it is COM1, we have selected COM1. Baud rate by default we choose 9600 baud rate because it's not too high and it's not too low. And interface is non-ISP because we are programming this through serial communication. And the second option one has to select is erase. This option should be selected. That means erase blocks used by hexa file. That means the flash memory should be erased whenever we load the hexa file. So this option has to be selected. And the third thing one has to do is go to options. In advanced options, in hardware configuration, do not use this DTR control and RST because we are not using modem control signals. So don't select this option, you unselect this option. So then once at least these 3 steps, this configuration is done, then through browse, whichever is the program you want to load it into the microcontroller, select that hexa file, right? So at this, in the previous example, we have written LED one example. So you can select that hexa file, say open. So once that hexa file is selected, then you, on your board, make sure ISP jumper is closed and you have pressed the reset button. Then you say start. So if the connection is okay, then this message will come. It says that reset the device into ISP mode. So now you will have to again press the reset button so that the communication will be established, and as you can see, the device will be erased and the microcontroller's flash memory will be programmed by using this hexa file. Once the programming is done, then it will show one message saying that it is finished. So once you get that finished, then again on microcontroller board you press the reset button. So then the application program which you have loaded, it will be start working. So as you can see, once the finished message appears on the screen, that means the controller is programmed. Then you can press the reset button and see the results that the LED is start blinking on the board, where in our case this LED should be on, which is connected in our design, as you can see, which is port 1.0, that is LED2 should be blinking. Similarly, we can see other example programs of assembly language program by using the same assembler, which are meant for multiple LEDs, LCD, serial communication, and so on. Okay, so the software folder, we have seen how to make use of 8051 IDE, that is the assembler, and we have seen the FlashMagic software to program the hexa file into the microcontroller's flash memory. Now let us see the C51 Keil compiler for writing the C programs as well as assembly language program and simulation and debugging. So this exe file you can download from the Keil software website, where evaluation version is available. You can say next, agree, next. So the software will be installed in the Keil directory. So I am saying C Keil, say 8051 is the folder I am creating. Then you can give some name. the installation will start. Installation is very simple. So add example projects to the recently used project list, say yes, and finish. So this completes the installation of the Keil compiler. Now we can start writing the programs. So Keil Microvision 3 is the one which we have installed for writing the 8051 programs. As you can see the Keil environment, where initially some example programs are installed in Keil 8051 directory. Hello.c is the main program. If you look at the left side of the screen, which is the project workspace, which is the project name is created, and then you can always add the source files as well as the assembly language. As far as this example program is concerned, your main program, as you can see, always starts with include the header files. Since we are using 89C51RD2, so register 52.h consists of all the CPU registers. And since this example is for using serial communication, it make use of printf and scanf statements. So that is why it is said include stdio.h. So where this printf and scanf functions are defined. And if you have any other variables, you can always define as a part of the main program, so that you need not refer them by hexa values. You can refer them by using some labels. So your as you can see, the void main is the entry of the main program, and then in the main program you are setting the port 1 as toggle, that is XOR. This is a logical operator to XOR with 0 1 of the contents of the port 1, and then you are using printf statement, so that whatever is written in the string in these quotes will be transmitted through serial port. So as far as the microcontrollers are concerned, printf means transmit the data serially, and scanf means receive the data serially through serial port. Okay. So once you have created the project, once you have example program you have typed, so the first step is you will have to say rebuild all the target file. So you should always say, it should say that 0 errors. That means your program doesn't have any syntax errors. And whenever you compile the program, it will also show how much data memory and program memory you have consumed as far as this program is concerned. So this is as far as the compilation is concerned. Now after that, if you want to simulate the program, then as you can see, there is a debug option is there. So this debug option is two ways. One is either by using the debug, you can download the program on the board and do the single stepping, or you can simulate the program. But online debugging is possible only if you have the Keil company's emulators. But in our case, we are using a third-party solution. So we are not using online debugging. We are using simulation environment. So for that, you can go to project and you can see the options for the Hello World, the project which you have selected. So let us not change the contents of these things. By default, we are using the default environment. But second time, if you go for options for the target simulator, this time it will show you which device you have selected, right? As you can see, 89C52 you have selected. If you are using some other controller, then you must change the target device. Similarly, what is the crystal frequency you have used on the board. If you have used a different crystal, then like in our case 11.059, then you must change the crystal frequency. And then let us not change any other options, because as you can see, say for example, off-chip code. That means on your board, if you have external memory, then you must specify what is the off-chip program memory, off-chip data memory. But since we are not used any external memory, we are using a single chip solution, let us not change even other options. As far as the output is concerned, whenever you compile the program, then hexa file will be created then you must say create hexa file. So you must tick this option. Then if the hexa file is created, what is the output file and where do you want to save that hexa file? You should give the path for that, so that after compilation the program will be saved in that location. Then we are not changing the other environment at this point of time because they are not significant. But what is important is in debug. In debug, now you have two options. One is use the simulator environment, other is use the Keil monitor driver. Since we are not using Keil company's proprietary board, so we are not using the Keil monitor driver, we are using the simulator environment. So this is the option one has to choose it. So once that is done, again you can compile your program. Now you see this time it will also say that hexa file is created. Now we want to go for the debug environment. As you can see, you can start the debugging. As it shows that you can maximum size of the code you can do debug is 2 kilobytes because we are using a evolution version. Once you say OK, then left side you can see the screen where you have the 8051, whichever is the target device you have selected, the CPU registers and the flags and other program counter and so on. Similarly, if you are interested in monitoring any other peripherals, then you can go to peripherals. Say for example, if you are interested in monitoring the ports or interested in monitoring the serial port, then you can keep on your screen which peripheral you want to view. And then similarly in view option, as you can see, you can also see your D-assembly window, logic analyzer, symbols, or serial terminal if you want to see. That means it acts as a computer serial terminal, as if the microcontroller is transmitting the data, and that data, some other terminal like computer serial terminal, it will show that what is the contents of the screen. See, if I say serial window, I have switched on. Now you can see this is my serial terminal. Okay. So now, like we have seen in that 8051 IDE, similarly here we have like real-time debugging options. Right now, though we have chosen simulation, but still, as you can say, single stepping, step over, and step into, step out of it, or run to cursor, all these options. So if I say, for example, in one shot, if you want to run the program, then you can run the program, or if you want to reset the microcontroller, then you can reset the program by pressing the reset button. So if I, for example, if I run the whole program, you can see I will run the whole program. That means now you can see the serial buffer, because we are writing the string into the serial buffer. The serial buffer contents are keep on changing. So that is how the peripheral is responding. But at the same time, we are sending on the serial port to the computer. So now, as we have discussed, that this software also has to view the status of the serial port. So now see, since we are sending hello world, so now it is showing that the other terminal, that is a computer, is also receiving this data as a hello world. So if you want to stop at any point of time, then there is a button to halt your program. As you can see, whenever you compile the program, it also shows that the C program, how it is converted into equivalent assembly language program. Okay, so this is how one can open a file, compile a file, then load a file and do the single stepping and view various peripherals of the CPU. Now let us see how to write a new project, how to create a new project, and then similarly do the same steps. So for that, you can go to the project. Let us stop the debugging. Then you can go to the project. Then you say always, you can say new project. This time we want to create our own project. For example, in the same examples folder, I want to create a new project. So create your own folder. Say for example, YSR is my name of the project folder. In this folder, so I'm giving my file name. So let us say LED is my name of the project file. If I say save, now see the second step, it is asking that which CPU you want to use. Now you see, though we are working for 8051 microcontroller, but still see how many companies are manufacturing 8051 microcontroller. Let me select, for example, Atmel company. See, in Atmel also, how many series of 8051 is there. If I say 89C51C ED2 IC2 ID2 RB2, so we are using 8089C51 RD2, say for example, you can choose this RD2, or 52 you are using, so you can choose 52. So the difference, what is the difference between one controller to other controller is, though architecture is same, but features are not same. Feature not are not same means, as you can see the left side description, it will talk about what is the operating speed, how many IO lines are there, how much amount of memory is there, how many peripherals are available. So all of them are architecture compatible. That means they are assembly language, instruction set, addressing modes, everything is same, but features are not same. Features are not same means number of IO ports are different. That means some of them are having 40 pins, some of them are having 44 pins, 68 pins, 128 pins. So packages are different, memory capacity is different, operating speed is different. So this will differ. So obviously, whenever you create a project, you have to carefully choose which target device you are writing the program. So then this fellow is asking that, do you want to add a startup code? Startup code means the compiler will add the initialization program of the hardware. So if you say yes, now you can see, if you expand your workspace, right, you can see startup.a51 file is created. So this is the source code created by the compiler. Now obviously, what do you mean by startup file for any programming environment? Startup file means, as you can see, first of all, it will initialize your interrupt vector table, right? So all the interrupt vector table locations are initialized. That means the minimum program required to initialize the memory is taken care by the startup files. Then if you doesn't want, like in our case, when we are initializing our own member location, then you need not worry about the interrupt vector table and the stack initialization, because in that case you can say you can remove the startup file, then you can add your own files, right? So let me add, now I created a project, but then I want to, if you want to create your own file, then you can go to the create a new file, then you can start typing your own program. Or else, if you are existing some already typed files are there, then you say add files to group. So in our case, say for example, if I have some files which are already stored in examples, right, just now we have seen the programs of hello world. So there is a C program, say for example, if I say add, then as you can see, the whatever is the existing file is a part of my main project. And if you have any dependencies are there, you can always left click, then right click, then you can always add any header files are there, then you can add or remove at any point of time. So this is the how one can create a project. And after creating the project, select the proper device. Once the device is selected, then either write entire new program, or if any existing C programs or assembly language programs are there, then you can add the C program or assembly language program. Once that is done, then second step is compilation of a program. So compilation is done by rebuild all target files. Once you rebuild target file, now you should see the output window. It should say that zero errors. That means syntax point of view, it doesn't have any errors. Otherwise, say for example, if I remove a semicolon here, then if I compile the program, now it says that target is not created, because in line number 43, syntax error is there in printf statement. So if either you can double click on the error message, then directly it will go there. The error is not in this line, the error is in this line, because it's not ended, not terminated properly. So similarly, for example, now if I compile it, no errors are there. But instead of that, if I say instead of port 1, if I say port 2, and if I compile the program, then there is no errors. But you want to send the data on port 1, but it's sending on port 2. This is not a syntax error, but it's a logical error. So logical errors cannot be verified by the compiler. Logical errors are verified by using the debug environment. Okay. So once your compilation is done, then I told you, you want to simulate the programs. Simulation of the programs is done by go to project. Now you select options for the group, say okay, then again go to options for the target. Now this time, first of all, you should create the hexa file, then go to debug and use the simulator environment. So once you compile the program, now hexa file is created. You go to debug environment. Now in this program, you are interested in seeing the contents of port 1. So go to peripherals, then you want to see the IO ports of port 1. So you can keep it the view of port 1 so that whenever this program is executed, the effect of port 1 can be reflected on this window. Similarly, you want to see, since you have used a printf statement, you want to see what is the output of the serial port. So you can go to view and serial window also you want to open and see. And in peripherals also you want to see serial port contents. Okay. So now if I either I can do single stepping or breakpoints, or in one shot I can run the program, say run. Now if I say run, now you can see since the program is port 1 contents or XOR operation is used. That means as you can see XOR with 0 1, so D0 bit will toggle. So similarly serial buffer we are continuously sending hello world, so the contents is getting modified. And since we are transmitting through serial port, this system also has a provision to show the contents on the serial port. So this is how you can view all the peripherals. If you have any modifications to be done in the program, stop the program, stop the debug environment, go to the main program. If you have any changes, say for example, this time I want to toggle the next LED, so select the next D1 bit instead of hello world. Then if you want to say something, some other thing, so say hello. Once the changes are made, compile the program. Since the remaining variables are already selected, directly you can go to the debug environment, say okay. Now you can, since your project one environment is already saved, you need not open the peripherals, they will be open automatically. Now if I run my program, now you can see the second bit is getting toggle, and then similarly serial window also you can see the string what we are transmitting now is also changed to hello. So this is how one can also use Keil as a compiler to write the C programs. Now we will see how to use assembly language program in the Keil environment. So in order to write a program assembly language in the Keil environment, the same procedure is adopted. You can select the project window, right click. If you have already written some assembly language program is there, say add files to the group. I have some couple of assembly language programs earlier we have written. So I'm using the same examples which were used 8051 IDE now. As since this time is assembly language program, instead of file type C, we will say .sr.a, which is a assembly language program. Now the same example I will open, that is the switching on the LED, which is on connected on port 1, so LED 1 assembly language program. So if I expand this project, the same example, which is port 1.0, set and clear the bits of the port 1. Right. So procedure is same. I can anytime compile this program. Now as you can see, the hexa file is created and 0 errors because the environment is same. Once my project space, as you can see, my project space is same. Now at the same time, I can also debug my program. I can go to simulation environment. This time, though my project name is same, but my environment is not same. So I'm no more interested in seeing the serial port or port 3. I'm interested in peripherals, which is the IO ports of port 1. I want to see when I execute the program. Right. So in this program, as we have already seen, port 1.0 will set or clear based on this delay. So like we can do single stepping, as you can see, same procedure. If I do step, then directly absolute jump, it will make a jump here. Then R0 right now is 0, 0. If I do a step, then it will execute this instruction that 7F will be loaded into this register. As you can see now, R0 is loaded with 7F. So that is how one can do single stepping. But at the same time, whenever you have a branch operations, then you cannot do single stepping because it will take those many times to complete that loop. In that case, you can step over the branch instructions. So if I skip that branch operation, then okay. So now if I execute the program, if I run the whole program, as you can see, the first bit of the port 1 is toggle because that is how our program is written. So the same compiler, Keil compiler, will work for assembly language programs as well as the C programs, or we can also see how to mix assembly language and C. And once the compilation is done, if you have simulated the program, if you are sure the program is working in simulation environment, then using the Flash Magic software, you can load the program on the board and verify. Okay, so let me explain you some of the example programs of various peripherals which can be interfaced to this microcontroller. So far we have seen one example, which one single LED which is connected on port 1.0 is getting toggle. Now let us see some more examples which are related to majorly to the ports. Then eventually we will see about the interrupts and timers and the external communication DAC ADC. In the second example, as you can see, the program structure remains same, that is interrupt vector table initialization, and by default the reset is the highest priority interrupt. So whenever program counter is loaded with 0, 0, we want to execute application program, that is our program. I kept the program structure same, like initially clear the internal memory, initialize the stack pointer, program counter. Only difference in this program is, instead of using the single bit of the port, in this example, entire port 1 is initialized as a output port where 0, 0 is loaded, and then first all the LEDs which are connected on the port will get FF, that is FF is immediate value is loaded in accumulator and outputted. A small delay is called, and then 0, 0 is loaded. So entire port 1 will get affected. So that's why this program we said 8-bit port, how to make it high or low. Rest of the code remains same. Okay, so this is for the interfacing 8 LEDs to the port. The next example is how to interface a relay to the microcontroller port. If you remember the circuit diagram, in the circuit diagram there is a transistor BC547 where a 12 volts power supply connected over here with freewheeling diode. So you can connect a DC relay which can operate at 12 volts. So the microcontroller is connected on port 1, 1.7, so that whenever you make it high, this transistor will be forward bias, relay will be get it energized. If you make it low, this transistor will be off, so relay will be de-energized in the off state. Before executing the program, make sure you have connected 12 volts DC power supply to this board, so that the relay gets the power supply. Also the microcontroller board gets the 5 volts power supply by using 7805 regulator. Okay, so in the program what you can see the changes for the relay is, rest of the code as I said is remain same. Only thing is, whenever you want to connect, wherever the relay is connected, for example in our case port 1.7 is clear, then after some delay we said port 1.7 is set. So then you will notice the delay is a slightly larger delay, so that instead of milliseconds, slightly we have taken into seconds, so that the relay won't get it jammed. So as you can see, there are 4 loops are there in the program to increase the delay. So what you can see in this program is that we are also clear the bit of 1.5, we also clear the bit of 1.0, because what I want to demonstrate is the relay switching of a relay, switching of a buzzer which is connected on port 1.5. As you can see, the buzzer is connected on port 1.5 and the LED which is connected on port 1.0. As far as the programming code is concerned, the code remains same whether you have connected a LED, whether you have connected a buzzer, whether you have connected a relay. Only difference is the driving capability of the port. Since it is limited, it can maximum can source 4 milliamperes and sink 20 milliamperes of current. So in case of a LED, we have directly connected to the port with 330 ohms resistor, so that it will limit the current to 10 milliamperes. Then similarly, in case of a relay, it requires more than 100 milliamperes of current. We have used a external transistor and 12 volts DC power supply. In case of a buzzer, since this is a DC buzzer, directly microcontroller can drive it. But however, if it is a slightly high power buzzer, then again you require an amplifier stage at this stage. Okay, so program remains same irrespective of what kind of control element you have connected to the microcontroller. Only thing is you will have to take care of the delay. Okay, now let us see how to interface the DC motor. As we have seen in our circuit diagram, there is a DC motor driver IC, that is L293D is there, which is connected to port 1.0 to 1.3, and the chip select signal for this L293D, that is enable, is connected on port 1.4. So in the program code, if you see the motor programming, in the program, right? So the initial part remains same. Only thing is, as you can see, first of all, since I have to enable the my DC motor chip select signal, that's L293D, as you can see, P1.4 set and clear. That means this will enable the IC or disable the IC. So that is as far as to make that motor on and off is concerned. But at the same time, since the motor is connected on the driver IC here on Q1 and Q2, so obviously port 1.0 and 1.1 will decide in which direction the motor will rotate. Say for example, if Q1 is high, Q2 is low, then motor will rotate in one direction. If you make it Q1 0 and Q2 1, the motor will rotate in other direction. Similarly, you can connect one more motor on Q3 and Q4. Okay, so that is why in this program, as you can see, 1.4 is acting as a enable signal, but however direction of the motor is decided by 1.0 and 1.1. In this case, in the first part, 1.0 is set and 1.1 is clear, but after some time delay, as you can see, slightly larger delay, 1.1 is reversed, right? Now this time 1.1 is set and 1.0 is clear. So the motor will start rotating in the opposite direction. So whether it is a LED or a relay or a DC motor, programming or setting the bits of the port or the language remains same. Now look at an example where we want to interface a stepper motor. The difference in DC motor and stepper motor is, in case of a stepper motor, you require all 4 outputs, because the stepper motor has 4 windings and one common wire which is connected to 12 volts. So how the stepper motor works is, once you select this IC by making pin P port 1.4 as an active high, then one bit of the port you have to set it high at a time. Say for example, if when Q1 is on, then other 3 bits should be off, and when Q2 is on, other 3 bits should be off, when Q3 is on, other bits will be off, and Q4, and then this whole cycle should be repeated in order to rotate the motor in, say, let us say, clockwise direction. If you want to rotate in counterclockwise direction, it is exactly opposite, where first Q1 is on, then Q3, then Q2, then Q1. Obviously, there should be a delay between one bit to set the one bit to the other set the other bit, is because the microcontroller can transfer that data in microseconds, but motors cannot spin or charge the discharge the coils in microseconds of time. It takes milliseconds. So there should be at least a milliseconds of delay in the program. Okay, now look at the program. Set bit P1.4 because that's where the enable signal is connected. Then as you can see, at a time only one winding we are energizing. Say for example, in this case we said port 1, that is D0 bit is 1, here D1 bit is 1, here D2 bit is 1, then D3 bit is 1. In all four cases we have made sure that 1.4, that is this bit, is always set, because unless the IC is enabled the data won't be accepted. So that bit is set, and then single winding is energized at a time, and then in between the steps we have called a delay, so that the motor won't be get it jammed. And then at the end we said repeat this step, so that the motor will be rotating in clockwise direction. Instead of 1 1, if you start with 1 8, then 1 4, then 1 2, then 1 1, then it will rotate in opposite direction. If you increase or decrease this delay value, then the speed of the stepper motor will be controlled. So this is how where a stepper motor can be interfaced to the microcontroller ports by using L293D IC. Okay. Now, so far what we have seen in this example is LED 1, LED 8, then DC motor, then relay stepper motor. Then we will see, so far in all these 5 examples, the commonality is all the IO ports are acting as a output port. Now let us see how to make the IO ports as a input as well as output. So in this example, we want to use the port 3 as a input port, and then whatever is the data available on port 3, we want to read it, and the same contents we want to write to port 0. So the difference in this program is port 3 we have loaded with FF, so that if once you load FF value in port 3, it will become as an input port, and by default port 0, by when you reset it is 0 0, it is an output port. So then as you can see in this program, we are reading the contents of port 3 loaded into accumulator, then accumulator contents directly we are writing port 0. So it will read port 0, port 3 contents and write to port 0, and then a slight delay will be there, and it is in the infinite loop, that is continuously this program will be repeated. So if you interface, let us say a few switches to the port 3, then it will read it, and then the same contents anyhow we have connected, or you can connect some LEDs there. So then you will see the effect that how the port 3 contents are reflecting on port 0. So this is how we can demonstrate how to make the port as a input port. Okay, then let us see how to interface a keyboard. You must have seen there are you can interface 4x1 keyboard or 4x4 keyboard, where whenever you are interfacing those keyboards, right, what we can see is that if it either you can interface the keys directly to the switches, to the IO lines, or you can interface the keyboard as a matrix form. In case of a matrix, it is like rows and columns, where you have to read the, you have to send the data, and then you have to read the data. Like say for example, row by row we select, we write some, let us say one at a time, one row will make it as active high, other rows will be active low, then we read the column data, then we will construct that into a some value, maybe some ASCII value or something like that, and then we can send it to the either LEDs, or if you have a LCD, we can display it. So this code, right, probably you can go through it, and you can implement where how a key press is converted into its key code form. Okay, so this I will leave it to you. Now let us see how to interface. Now the next example is how to interface a LCD. As we have seen in our design, the LCD, which is 16 by 2 LCD, you can connect it on this connector, where port 2 is used for transferring the data, and port 3.5, 3.6, 3.7 is for connecting the control signals or the handshake signals. Okay, so in the program, the interesting part of LCD is, because LCD itself is having some memory, LCD also has some controller inbuilt. So before you send any data or text on LCD, one has to first reset the LCD. So whenever you want to reset the LCD, as you can see, 30, I mean that is the software reset, this is called software reset. So 30, 30, 30, 3 times we write to the port of the port 2. That is because that is where the LCD is connected. And then we call command. Command means these are the handshake signals. Say for example, as you can see, where are the handshake signals? Port 3.5, 3.6 and 3.7, where RS read oblique write bar enable signals are connected. So whenever we write a command to the LCD, what you can see is that this RS, that is the register select signal, is clear. That means port 3.7 has to be clear. And read oblique write bar, as you can see, first we clear, then we say enable, we set it and we clear it. So this is the sequence whenever you send a command. So I repeat again that since handshake signals in our design is they are there on RS is connected to port 3.7, read oblique write bar is connected to 3.6, enable is connected to 3.5. So the sequence is whenever you send a command to the port 2 data bus, 3.7 has to be 0. And whenever you send a data to the port 2, 3.7 has to be 1. And that is called register selection. So that whenever you send a command, the registers of the control registers has to be selected. And whenever you send a data, then the data registers, that is RAM, has to be selected. So port 3.7, pin 3.7 decides whether to select the control registers or to select the data registers. That is how LCD will differentiate between the control words and the data. Then about the other pin 3.6 is called read oblique write bar. So in order to tell the LCD that the data is available on the data bus, this read oblique write bar has to be active low, so that the LCD will accept either command or data. In both the cases, read oblique write bar has to be active low. And the third is the handshake signal, that is P3.5, which is enable. Enable is like a latch enable. Whenever you write the data, first of all it has to be active high, then active low, so that the contents on the data bus has to be loaded. So these two signals, their status remains same whether you send command or data, but this signal, that is RS signal, is 0 if you are sending command and 1 if you are sending data. So as you can see in our functions, whenever I am sending command, this 3.7 is, that is register selection is 0, and whenever I am sending data, as you can see 3.7 is 1, and rest of the control signals remain same. Okay, so since 30, 30, 33 times when I am sending, it is a command to reset the LCD, which is a software reset. So whenever I am sending the command, as you can see, I am calling the function command 3 times because it's a command to reset the LCD. Once the reset is done, then we will have to send few control words to the LCD. For example, 38. 30 is the selection, function selection of the LCD. Then 30 is to switch on the display on, and then, display shift and the cursor on. That is for 30, is again a command word. Then to make the display on, you will have to send the 0C. So this is how a LCD, 8-bit LCD is get it initialized, or you can refer the data sheet because LCD is a universal. Any LCD data sheet, 16 by 2 LCD, if you refer, the data sheet says that 33 times you will have to send. Then based on your size of the font, you want to blink the cursor, and if you want to switch on the display accordingly, the control words are given in the data sheet, where you'll have to send 3830C to the LCD port 2. Okay, then once this is done, okay, the next control word for the LCD is we want to clear the contents of the LCD. We want blank. So for that, the data sheet says that whenever you write 01 to the data bus of um, the LCD, then that command will clear the contents of the LCD. Okay, the next command is 80. 80 is to select the row. Whenever you send 80, then whatever you want to display, that will be displayed on the first line. And if you want to display on the second line, then you will have to, instead of 80, you will have to send C0. So this is the address, RAM address of the LCD. 80 to 8F is the address of the first line. C0 to CF is the address of the second line. So in our example, we want to display it on the first line. So we are sending 80 address to the port 2, which is again a command. So far, all these things are commands. That is, reset the LCD, then enable the LCD, then select the cursor, display on, clear the LCD, select the first line is the command. Now we want to send the data. Data is always in ASCII form. Whatever you want to display it on the LCD is a ASCII values. So for example, in this case, if I want to display A, so I have for A, the equivalent ASCII value is 41. So as you can see, 41 is right. We are writing to the same port, but only difference here is that instead of calling the command, this time now I am calling the date. That is nothing but, as you can see, I am calling this function. In this function, what is the difference as compared to this function is only one bit, that is P3.7 is active high, because the register selection has to be active high, so that LCD will recognize that when you are writing 41, this is not command, this is a data. Okay. After that, once it displays a character on LCD, then we says that infinite loop, short jump to BK. So it will just a halt. So this example will demonstrate that on LCD, on first line, first column, a character will be displayed. So this is how you can interface a 8-bit 16 by 2 text LCD to the microcontroller port 2 and port 3. Now second example is more or less same. The entire program is same, like initialization and the selection of the first row. Everything is same, but a small change. That is, only change is, say for example, you have defined some data in the microcontroller. As you can see in assembly language, to define the data, there is a db directive is there, define byte. Then in quotes, whatever you mention, that will be converted into ASCII value. And we have assigned a label on the left hand side. So this label act as a memory address to the memory where this hello is stored. Okay, now this address, what we are doing in the as this microcontroller has a RAM space, which is a data memory. So being a Harvard architecture, program memory is different and data memory is different. So we have initialized the DPTR with the address of the memory location where the data is stored. So once the DPTR loaded and accumulator is 00, so DPTR plus accumulator, that means the first memory location contents are loaded into accumulator, and that we are transferring to port 2. So it is act as a memory pointer where my data is stored, and then DPTR has the address and accumulator has the offset 00. And every time, as you can see, we are incrementing the DPTR so that it will either you can increment the DPTR or you can increment the accumulator, but any one of them. So in our case, we are incrementing the DPTR so that it will go to the next location, and offset value is just we have selected as a 00, add to the DPTR. So resultant address, that is the next location contents, will be loaded into accumulator, and then we are sending to the port 2, which is the data. So till the last character we have repeated. You can write a small loop also where you can put it in a conditional statement, but just to demonstrate that how data is retrieved from the memory like a lookup table. In this example, whatever is the data is defined here is loaded or fetched from the data memory by using DPTR, just to demonstrate how you can define the variables in the program which is stored in the data memory space. So this is about so far we talked about how to interface the LCD how to interface keyboard to the microcontroller ports. Okay. So similarly, I told you all of you to think of keyboard programming in a scanned mode, where whenever a key is pressed, then how to convert into a ASCII value. So once this logical program, if you develop it, why don't you use the LCD program? Because basically you already tested LCD program. So by using this LCD program, whichever is the key is pressed, then the contents of that key, that is ASCII value, should be displayed on the LCD. So we are trying to merge two programs so that the keyboard scanning and as well as the LCD interface both are being tested. So this is what is so far without using any peripherals, just by using IO ports, we have written at least around 9 programs. Okay. Now let us see how to use the other peripherals of the microcontroller. So one of the peripherals we have already seen, that is the IO ports. Now let us see the next peripheral, which is the interrupt of the microcontroller. Interrupts are, as you know, they are there on the IO ports, right? As you can see, the microcontroller has interrupts. Say for example, port 3.2 and 3.3, right? These are having not only IO ports, but they're also having hardware interrupts, that is INT0 and INT1. They are the hardware interrupts. But incidentally, in our case, the same switches we have also connected, right, S1 and S2 to the not only as a IO ports but also as a interrupts. That means whenever you press the switch, you can also sense whether it is a active high or active low by using not as a IO lines, as a interrupt pins, external interrupt pins. So what is the difference in writing the program? The difference is, in case of IO ports, if you are reading the IO lines, then we read the program, we read the IO ports in a pooling mechanism. But whereas you will see in this case, our program is not in pooling mode. That means it is not continuously reading the status of P3.2 and 3.3. The main program is free, where the some background loop, it may be in the background loop, and then some foreground program will execute as and when the pin is sensed with active low signal. So let us look at the program structure in interrupt. Okay, so far our program structure remains same, but you will surprised to see that the second ORG statement, that is 003H in interrupt vector table, instead of saying written from interrupt, this time we said absolute jump to ISR IE0, that is the external interrupt 0 ISR. So that means what will happen whenever a interrupt is received, right? Obviously the microcontroller will start executing this location. In this location, what is written is absolute jump to this label. This label is nothing but it will come here, right? Like we have seen, whenever reset is microcontroller receives, then it will make an absolute jump to start, right? That is the highest priority. But after that, now we will see that two more interrupts we are using. One is interrupt 0, and then we are using interrupt 1. So interrupt vector location for IE0 is 03, and for IE1 it is 13. So what is that we have written in IE0 is that whenever a interrupt is sensed, that means whenever port 3, that is in our hardware, whenever port 3.2, whenever this is sensed, then INT0 interrupt vector program, that is called ISR, will be executed. Whenever port 3.3 is detected, which is INT1, the program will be executed. Like you can see two ISRs. What is written in ISR IE0 is set the bit of port 1.0, because as we know, we have connected a LED in our system, right? This LED, first LED, LED2 will be on, and if second interrupt, that means when second switch is pressed, then the same bit will be cleared. But what you can notice is that this is not a function call. In function call, like say for example, you can see we always use a return instruction. That means return from the function. But whereas in case of the interrupt, what you can see is that it is return from interrupt, because it is not a function. It is a interrupt service routine, and interrupt service routine is not a planned one. It is an unplanned one. It is asynchronous system. So whenever this interrupt is received, then only this function will be called, otherwise no, right? And then so when you say return from interrupt, so then it will, from wherever it has left, it will come back to the main program, because it is unplanned. The interrupt may come here, it may come here, it may come here, it can come anywhere. So it has to return to the place where it has left. So it is an unplanned event. My rest of the program is same, but as you can see again, my since I'm using the LED port 1, I have made it as a output port. Then port 1, the other bits, right, where the where switches are connected, that has to be a input port. Okay. Now since the port 3 in our case is not just interrupts, right? Then it's not just a IO ports, it is interrupts. Okay, so that is why we'll have to initialize the interrupts. So if you refer the data sheets of the external interrupts INT0 and INT1, there are registers called TCON and IE registers. They have to be unmasked and they have to be enabled, and one of the interrupt has to be given highest priority, so that if both of them are received simultaneously, one of them will be acknowledged first. And then as you can see, long jump to dollar symbol. So dollar symbol means jump on its own, so it won't go anywhere. It is a hanging. So this is what I was trying to say, that this is called background loop. So it is doing nothing. Once we initialize the interrupts, do nothing. So that means this LED won't be on and off because of your main program. It will be on and off only when the interrupt comes. So that means your main program is free, doing nothing. So that is the difference between a pooling mechanism and a interrupt mechanism. In case of a pooling mechanism, as you can see, we are continuously in the infinite loop. So the CPU is continuously busy in reading the port and writing to the port. But whereas in interrupt mechanism, you are doing nothing. A long jump to on its own means it's like an infinite loop, do nothing. So that means you can also do some other programs. So whenever you want to implement multitasking environment, better to make use of the interrupts, is because as and when the service is required, that time only the service routine will be called. Otherwise, whereas pooling mechanism, the CPU cannot do any other job except to read the readiness of the input-output devices. So these are the two ways of data transfer methods as far as the conventional microcontrollers are concerned. Okay, so this is the second peripheral. I would like to introduce you that how to use the interrupt or event manager mechanism of the microcontroller. The third peripheral I want to introduce is the serial communication. As we have discussed in the microcontroller, there is a RxD and TXD pin where the data is transmitted through serially. That means 8-bit data, once you program it, then the whole data will be transmitted or received through serially. So this communication is called asynchronous communication, because as you know, nowhere we are using the clock. Only we are either transmitting or receiving the data through this MAX232 IC driver to either you can connect to the computer serial port, or else if you want to directly connect a Bluetooth or other microcontroller, then you don't require the driver IC. Directly the TXD pin you can connect it to RxD pin of the other controller, and RxD pin you can connect to TXD. Or if you want to make a null modem, then directly short circuit the TXD pin to the RxD pin, so that whatever is transmitted will be received back. So that way also you can test your programs. Okay, so whenever you want to use this peripheral, so the most important thing as far as the initialization is concerned is the setting the baud rate of the serial port. Means one has to set what is the rate of communication, and then one has to enable whether you want to transmit or receive. So these are the control registers to set the baud rate and to enable the transmitter as well as the receiver for serial communication. So as I always said, hardware initialization. Once the hardware initialization is done, okay, now the serial port peripheral is ready for communication. Whatever you want to transmit, always you have to write to SBUF register, and whatever you want to receive, always you have to read from SBUF register. In this example, continuously we want to transmit a character 31, that is a ASCII value 31. That means 0 will be continuously we want to transmit on the serial port. So the contents we write to SBUF register, and then since the serial communications takes some time to convert parallel to serial form, then we are verifying whether the TI bit is set or not. So TI bit will be set only when the SBUF register is empty. SBUF register will be empty only when the data is converted parallel to serial form. Once that is done, then it will come out of the loop. Then after slight delay, we are repeating. That means same character again and again with whatever is the delay you have called will be continuously transmitted. So this is how you can verify how serial communication is happening. Like I said, you can also use the serial terminal. Say for example, if you look at the flash magic software which you are using to transmit to write the program on the board, this tool also has a provision to monitor computer serial port. So once you load the program onto your target device, then immediately you can go to the tools, open the terminal. Now once you open the terminal, as you can see, you will have to select COM port and same baud rate, whatever your program you have set, same baud rate you select, and if you say OK, now as you can see a new window will be opened. So whatever is your microcontroller transmitting, the data will be appeared here. Or if you want to send any data to the microcontroller, you type here, microcontroller will receive. So that is how you can two systems. One is the computer terminal, other is the microcontroller. Both can communicate the in full duplex form. So that will help you, so that computer, as far as the computer is concerned, you don't need any another software to initialize the computer serial port. That is taken care by this flash magic terminal itself, that is setting the baud rate and setting the full duplex. That is a complete communication protocol. Okay, so once you verify how communication is happening, then we will see the next example. The next example is, can we interface a D to A converter or A to D converter to the microcontroller? Like say for example, as we know, so far whenever we write the data to the microcontroller ports, the data is always in digital form. But is there any way to convert the data into analog form? Since 8051 microcontroller doesn't have inbuilt D2A converter, so externally one can interface the D2A converter. And then for example, in this case, you will notice that we have connected port 2, DAC. If you connect it in your this thing, the connectors are there. So on port 2, using FRC, you can interface AD558 or 0800 8-bit DTA converter. Then you can write a program where, for example, we are sending 00, then we are incrementing the accumulator and with a delay. So that means whenever you write a digital value to the port 2, then we call a delay, and then we are in infinite loop. That means the value will start from 00, will go up to FF, and then after FF, if it increments, then suddenly it will fall down to 0. That means as if you are generating a sawtooth waveform. So the frequency of the sawtooth waveform depends on the delay, how much delay you have added, and the amplitude of the sawtooth waveform depends on up to what value you have incremented this. So that is how you can control the amplitude as well as the frequency of the signal. So you can use a oscilloscope and you can see on the DAC output that the digital value, whatever we output to the port 2, where the DTA converter will convert into analog form, and then you can observe on the CRO. Similarly, you can modify this program to generate triangular waveform or a sine waveform or some complex waveforms like ECG, EMG signals. Okay, so this is the example to demonstrate how one can interface D to A converter to the ports of the microcontroller. The opposite case is A to D converter. As we know, opposite case means if a analog signal, say for example, if you have any sensors, sensor like temperature sensors, pressure sensor, humidity, radiation. So such type of sensors, if they are there, if the signal is in analog form, maybe millivolts or volts, so then how to convert its equivalent value in digital form? So again, the conventional 8051 microcontrollers doesn't have inbuilt A to D converter, so we'll have to interface a external ADC. Popularly, ADC 0809 is used, which is a 8-bit, 8-channel A to D converter where successive approximation technique is being used. It's a very popular A to D converter because for several years it is in the market. Okay, so if you carefully look at the interfacing part, it is having first of all 8 data lines, so that whenever analog to digital conversion is done, one can read the 8-bit data. But at the same time, it is also having handshake signals. Handshake signals means, as you can see, start, address latch enable, output enable, end of conversion, and selection, channel select signal. So it is a slightly complex ADC is because it uses successive approximation technique for converting analog to digital form. So just to begin with, say for example, being a successive approximation ADC, you require a clock source to convert analog to digital form. So a 555 IC one can use to generate the clock for this ADC. So with this clock, it will convert analog data into digital form. There are 8 channels are there. So you can connect to 8 analog inputs. Like one channel can be temperature, other pressure, radiation, humidity, displacement. Like that, you can connect 8 channels. But at a time, the A to D converter can convert one analog signal into digital form. At a time, only one. So how to select which channel data you want to convert analog to digital form? For that, as you can see, there are 3 address lines are there, like A0, A1, and A2. Say for example, assuming that in our board, if you connect port 3.2, 3.3, 3.4 to the address selection, so if these 3 bits are 0, 0, 0, that means IN0, that means channel number 0 is selected. If it is 0, 0, 1, then next channel will be selected. If all of them are 1, last channel will be selected. So before you give any control signals, first of all, you have to select the channel. So that means first give the address, put the address on the channel so that a specific channel will be selected. Once that is done, then on P3.5, you have to say that start and address latch enable. That means we are telling the A to D converter address is there, so channel is selected. Then start means you convert this analog data into digital form. So then this ADC will take some time, that depends on the operating speed, will convert the corresponding analog channel into its equivalent digital form. Once the conversion is done, then how the microcontroller will come to know. So there is a feedback signal is there. As you can see, what is called end of conversion. End of conversion means now this bit will tell that whether the conversion is still happening or conversion is completed. Once the conversion is completed, if the signal is sensed, then you have to say output enable, so that the ADC will put the data on the data bus, right? So this is the sequence. First put the address on the address bus, channel will be selected, give the start signal, and we have shorted start and address latch enable together. So make P3.5 as a active high, so that conversion will start converting. And then this is input, remember, end of conversion is input. That means you will have to read port 3.7, whether it is active high or active low. Then once the conversion is done, then port 3.6 you make it active high, so that the ADC will put the data on the data bus, and the data bus we have connected to port 2 of the microcontroller 08051, then read the data as a input. So then just to demonstrate, the same data we are writing to the port 0 where you can connect 8 LEDs. So it depends on the amplitude of the input signal. These LEDs will show what is the status. Or at the same time, you can also use LCD to display the data, or serial port to transmit the data, whatever. So in short, how many ports we have used in 8051 to use to interface 8-bit ADC is port 2 for data, port 3 for address and handshake signals, and then just to write the data to some other ports we have used port 0. Okay, now look at the program, how the program is done. So initial part is same, that is interrupt vector table is initialized, then we have cleared the memory, stack pointer is initialized. Okay, now after that, as we have discussed, port 0 we have used for LEDs interfacing. So 00 is loaded so that it will act as output port. Then port 3, there only one bit is input, rest are output, because end of conversion is input. We'll have to read the status of the end of conversion. So that is why 80 if you write it. Then in port 7, port 3.7 will act as a input port. Then port 2, data of the ADC is connected, so we made it as a input port by writing entire port as a FF. So this is the port configuration where input or output has to be done based on our application. Once that is done, now you can see how to select a channel. Channel selection is done by port 3.2, 3.3, 3.4, where the A to D converter address bus is connected. So in this case, we want to select channel number 0. So we made all the bits as a 0. Then you will have to give the start and address latch enable, which is set the bit of the port 3.5, so that that particular bit will make it as active high and a slight delay, and then clear the bit so that it generates a pulse of a small duration, which will trigger the A to D converter to convert analog to digital form. But then every ADC will take some time to convert, because this is a digitally operated. So how the microcontroller knows whether the conversion is completed or not? So as you can see, once the start pulse is given, then we are reading the port 3, and then we have used a logical operation AND instruction to AND with 80 value, so that all other bits will be masked except the last bit, because we are interested in knowing what is the status of port 3.7. So if this signal is 0, so we are verifying compare jump if not equal to 80. That means if it is not 80, right, it is continuously in the loop. If it is 0, that means A to D converter has not completed its conversion. If it is active high, then the condition won't be satisfied, then it will come out of the loop. So once it is come out of the loop, then how to tell the ADC to put the data on the data bus? So as you can see, the set bit, that is port 3.6, where output enable signal is connected, so that the latch will be enabled, ADC will put the data on the data bus. So now, since the data is available on the data bus, we are reading the port 2 of the microcontroller, and those contents we are writing to port 0, so that the same contents will be transferred to port 0, so that LEDs or whatever is connected will indicate. And then since we want to do this continuously, long jump to again, that means this entire selection of the address, then start, then end of conversion, output enable, read the data, has to be in the continuous loop, so that this A to D converter is keep on converting analog to digital form. So these are some few examples which will demonstrate how to make use of 8051 as a microcontroller based system, which demonstrate almost all the external peripherals like LEDs, LCDs, switches, keyboards, and then we also seen how to interface relays, DC motors, stepper motors, and then we also seen the internal peripherals apart from the IO ports. We also seen how to make use of the interrupts, serial communication. Now last peripheral I would like to show you, that is about the timer. Though we have used the timer in case of the serial communication. If you want to generate, say for example, PWM signal, right? Now this example demonstrates just a application, so that most of the speed control are inverters, UPS, where we always talk about how to control the width of a pulse by using timers. So this example shows that again we have used in we have initialized the interrupt vector table. Now interestingly, you can see this time the interrupt vector table, that is 0 0 is reset, but see 0b is in timer 0 interrupt, and 1b is timer 1 interrupt. So we are using now in this example microcontrollers, two timers, timer 0 and timer 1. Now whenever the timer 0 overflows, right, then it will make a jump to this interrupt service routine, which is nothing but this. And whenever timer 1 overflows, then it will make a jump to INT1, that is this. Okay. What do you mean by overflow? Overflow means whatever is the clock you have connected to the timer and whatever is the count you have loaded into the timer, once it reaches the maximum count, say for example 0 0 is the initial count, when it reaches the maximum count, means when it reaches FF, then a interrupt will be generated. So that is called, that is the meaning of timer overflow. So when the overflow occurs, then the microcontroller will execute this instruction. This instruction is nothing but make a jump to the interrupt service routine. Okay. So that means we are using two timers so that whenever they overflow, two interrupt service routines, this is one, and this is the IN timer 0 interrupt service routines will be executed. But how will you come to know that the timers are generating the interrupts? So what we are doing is we are using port 3.7 as a indicator, so that if you connect a oscilloscope on port 3.7, then in one interrupt service routine, as you can see, port 3.7 bit will be set, and in other interrupt service routine, port 3.7 bit will be clear. So then we will come to know what is the rate of execution of timer 0 and what is the rate of execution of timer 1. So one will set the bit, other will clear the bit, that will indicate the width of the pulse is being controlled by the timer 0 and timer 1. Okay. Then how to load the width of the pulse? How will you vary the width of the pulse? So what is done in this program is that in the data pointer, whatever is the width you want, the period value is defined here. Some let us say some count of B1 E0. Let us say we have calculated for 20 milliseconds. This is the count. So when your microcontroller is operating on 12 megahertz, if every count takes 12 clock cycles, that means you can calculate how much amount of count is required, so that that count, once you load it, then it comes out to be around 20 milliseconds. Okay. So if this count, if you load it, as you can see, DP data pointer, we have loaded first here the period value, and in timer 1, the TH and TL, we have loaded those count, the total period into this register. That is as far as the timer 1 initialization is concerned. And timer 0 initialization is concerned, what we are doing is the LSB permanently we have loaded 0 0, but MSB, what you can see, MSB we are loading through the port. What you can see is that we are reading the port 2 contents, and then we are writing into, let us say, TH0, that is the MSB part. So that means the one timer contents are programmed in the program itself, but other timer contents, user can load that value by using the port 2. Say for example, if you connect some 8 switches on port 2, then the port will read the contents of this and will write it to the timer TH0. So then you will find, you will notice that the width of the port 3.7 is controlled by these 8 switches. Okay, so that is why in the main program, in the main loop, what you can see is the timer 1 and timer 0 is initialized, and then port 2 is initialized as a input port. Then once that is done, Then we are enable the timer 1 as well as timer 0. Both the timers we have started, and initially set the bit of 3.7. And once you start the timer, now as you can see, do nothing. This is again in the background loop. So that means in sjump to dollar means do nothing, wait infinitely. But whenever the timer overflows, then either this interrupt or this interrupt, based on which timer is overflow, that particular service routine will be executed. So this program will demonstrate that two timers are simultaneously working. That is the actual meaning of concurrency. And then just to demonstrate the how to vary the width of the pulse by using the timer, where in the service routines we have used the port 3.7 bit, so that by user can modify the contents. Okay, so this will demonstrate almost all the, with this example we have demonstrated almost all the peripherals of the microcontroller, that is right from IO ports, interrupts, serial communication and timers. And similarly we also seen the external peripherals. I think this will be a useful uh, examples for in the beginning stage of the students, so that whenever they develop the projects, almost somewhere or the other they can make use of these input output devices and the peripherals.